Hey guys, this is section 1.1 and here we go. So here we're going to formally talk about interval notation, which we actually have been using. So let's go ahead and get started with the first few over here. This table describes, how to convert between set notation, which you're used to, and inequalities, or the interval notation. So if you take example number 1a, if we want our interval to be from -2 to 12, including both numbers, we say that's -2 to 12, close the brackets. For something like x is greater than -17, we say the values start at -17 and they go up to positive infinity. Infinity is always open, and since this is just greater than, not greater than or equal to, we say open as well. Here, so it's x is less than 3 or greater than or equal to 8. So for the first part, we say it's -infinity to 3, and then or we say union for this. Okay, so that's just a union, 8 to infinity, but the 8 is closed, so we put a square bracket. Here, x is less than 0, that's -infinity to 0. All right, so let's move on to what a function is. A function is a way to map relations from one set to another set. The thing that makes a relation a function is that every value in the input can be paired to only one value in the output. The best way to test whether something is a function is by doing the vertical line test. That is, you can draw vertical lines, imaginary vertical lines, a series of them, through a function. And if each of those vertical lines passes through the function once only, then it's a function. So, so this is clearly a function. And if there was another point here, then a vertical line would pass through more than one, and that would fail the test. It would not be a function, right? So that would mean that each input, each x value has two y values. So that doesn't work. All right, if we go here to see if this is a function, you see that if you look at the x values, none of them repeat. So yes, it's a function. Here, you see that the x values do repeat, and what's more, one of the twos maps to 0, one of them maps to a different value, 5, so this is not a function. This one definitely passes the horizontal line test, so it's a function. Okay, this one, right, let's solve that for y. I divide by 2, I divide by 2, x over 2 is equal to y squared. Let's take a square root of both sides. So what I get now is y is plus or minus root x over 2, meaning y has two values. Positive x over 2, negative x over 2. So when you graph this, you actually have the positive root x over 2, the negative root x over 2. Clearly, it fails the horizontal line test, so it's a no. Also, if you put in an x value here, suppose you said, okay, what if x is equal to 2, right? Put it in the equation. If you solve this for y, you get 1 equals y squared, so y is plus or minus 1. And as long as you get two y values for one x value, it is not a function. Okay, let's go to function notation. I know you remember this from Algebra 2. F of x is function notation. This tells you the name of the function is f, and that the variable, independent variable used in the function is x. Okay, it is interchangeable. F of x is interchangeable with y. When you have y equals f of x, like we said, x represents the values of the domain, and that's called the independent variable. The values that y takes on are the range, and they're called the dependent variable. Okay, so here we have something that we've actually done before. We need to find for each function, first we need to find f of a, and then second we need to find this other one. So this is really like part A and part B. Okay, so let's do part A here. Part A says if this is f of x, then I need to find f of a. Well, how do I do that? X gets replaced by a, and I get a squared minus 2a. Okay, that's all for part A. Now for part B, I'll do that with another color. For part B, what I want is this whole mess. Okay, so what I want is f of a plus h minus f of a over h. Now that is made up of three components, 1, 2, 3. This is just like what we were doing in chapter 5 with the sines and the cosines, sine of x plus h minus sine of x, and so on. So for number 1, let's find f of a plus h. If f of x is the same f of x that we were using, then what's f of a plus h? Well, that is a plus h squared minus h a plus h, right? So I'm substituting for x a plus h. So this is, if I multiply that in, a squared plus 2ah plus h squared minus ha minus h squared. Okay, now what happens? H squared and negative h squared goes away. So this is a squared plus 2ah minus ah is plus ah. Okay, so let's go back here and put that stuff in there. I was supposed to have found f of a plus h, which I just did. It's a squared plus ah minus, now I need f of a. What's f of a? I had actually found it before here. So f of a is a squared minus 2a all over h. And now I need to simplify that a little bit more. So it's a squared plus ah minus a squared plus 2a all over h. These go away, and I have 2a plus ah over h left over. Okay, all right, so let's do another one here. For f of x, I need to find f of a. For f of x equals 3. Well, let's take a look at what f of x equals 3 looks like. If this is the x and y axis, f of x equals 3 is like graphing y equals 3. So now, what's f of a? Well, no matter what the x value is, whether it's 1 or 2 or a, f of a is equal to 3. right? This is a constant function, so no matter what, it's going to be the same. F of A is 3, F of C is 3, F of 4 is 3, F of table is 3. So for part B, let's now find F of A plus H minus F of A over H. F of A plus H is 3, minus F of A is 3, over H is 3. So this is 0 over H, 0. Okay? All right. Let's talk about domain. All right. A function with an unspecified domain is called the implied domain, which means if you just see a random function right out in the open, you're walking down the street, you see a billboard with a random function on it. The values of x, which that function exists over, is called the implied domain of that function. Basically what you know as domain of the function. Okay, how do we find the domain of a function? Well, first, the easiest way is to exclude the values from the domain over which that function is undefined, which means exclude the values which will result in you dividing by 0 or taking the even root of a negative number. Okay, so for example, let's take a look here. Look at these examples. If you have this first function, x squared minus 4 over x plus 2, immediately we see a problem with the denominator. Because once the denominator is 0, this function is undefined. Well, where is the denominator 0? At x equals negative 2. So we say that this function exists over all numbers except negative 2, right? So negative infinity to negative 2, we're cool. Negative 2 to positive infinity, we're cool. And that is how we express that. When we talk about root x minus 2, we need to make that function such that this number inside is always positive, right? X minus 2 should always be greater than or equal to 0. So x should always be greater than or equal to 2, which means the domain is 2 to positive infinity. Okay. Let's talk about domain. We're going to separate this into a couple of different parts. First, we're going to talk about polynomial functions. These are everybody's favorite function, okay? Polynomial functions, you basically have x to the power of some integer, x to the 1, x to the 0, 2, 3, 4, and so on. The domain of all polynomial functions is all real numbers. Best case scenario. So look at part A, polynomial function, domain is all reals. Look at B, polynomial function, domain is all reals. There is no x value that you can't plug into that function. Okay, now what's a little bit more interesting is rational functions. These are functions that have a variable in the denominator. The domain is every number except the zeros of the denominator. So what you want to do for any one of these is factor out the denominator. So let's factor this denominator. We're going to get x plus 4, x minus 3. Okay, where do these equal 0? At negative 4, right? So you say x plus 4 equals 0, x equals negative 4, x minus 3 equals 0 at x equals 3. So you have to exclude those numbers which make the denominator 0. That means I'm cutting out negative 4, I'm cutting out positive 3. So which of these regions work? this one, this one, this one. How do I write those? The leftmost region is negative infinity to negative 4. Union. Middle region, negative 4 to 3. Union. 3 to infinity. That is the domain. Look at this next one. They're already factored out. So, okay, where is this equal to 0? At x equals negative 8. Where is this equal to 0? At x equals positive 10. So, negative 8 and 10 don't work. Everything else will work. So I say the domain is negative infinity to negative 8, negative 8 to 10, 10 to infinity. Do you have to draw this number line every time? Not at all. I'm just drawing it for you guys to see. Okay, let's take a look at this next one. Let's see where this denominator is equal to 0. Okay, we subtract 1. X squared is equal to negative 1. Take a square root, take a square root. X is plus or minus the square root of negative 1. X is plus or minus I. Oh my, what happened? It turns out there are no real numbers for which this denominator is 0. In other words, this denominator can never be 0. In other words, because there is no number for which this is 0, the domain is all real numbers. Any old number that you plug in there will work. Okay, let's talk about radical functions. So here, for radical functions, okay, this is important now. The domain of a radical function which has an even nth root is the numbers for which the radicand, the stuff inside, is greater than or equal to 0. If it's an odd root, then it's all real numbers, right? So if you have the square root of x, the stuff inside the root here can only be greater than or equal to 0. Okay? Negative 5 won't work. But if you have cube root of x, any number that you put in there will work. So the domain for y equals root x is just the positive numbers, but y equals cube root x is all numbers. Okay, so what do you do when you see a root? Let's just get down to it. When I see a root, I take the radicand and I say, okay, that number has to be greater than or equal to 0. And then it just becomes a little old algebra 2 problem, right? 7x is greater than or equal to 70. X is greater than or equal to 10. So I say my domain is from 10 to infinity. Okay, this one's a little bit trickier because it's x squared minus 2x minus 15. First step is the same. That has to be greater than 0. But the difference here is that this is a nonlinear function, not x to the 1, but x to the 2. This has its own process. What we do is factor this guy first, and we extract the points, right, where each of these parentheses will be equal to 0. Now I put those points on a number line to create a sign chart. You should have done this last year. Chances are you forgot. So what we're going to do now is this. Notice the -3 and the 5 divided this number line into 3 separate regions. What I'm going to do is plug in a point from each of the regions into the function and see whether or not I'm going to get a positive or a negative number. Okay, so first I plug in from the leftmost region, -5. Well, if I plug that into the first parenthesis, that gives me -5 minus 5, a negative number. Second parenthesis, -5 plus 3, another negative number. Negative times negative is positive, so I get a positive number. Next, let's plug in something between -3 and 5, like 0. The first parenthesis gives me 0 minus 5, negative number. Second parenthesis gives me 0 plus 3, positive number. Negative times negative is negative, so that gives me negative. Lastly, if I plug in a number to the right of 5, like 10, both of the parentheses will give you positive values, so that means positive times positive is positive. Okay, what does this mean? Remember way back when we had said we wanted the stuff inside the root to be positive or greater than or equal to 0? Well, which regions did that happen in? This region and this region. Okay, for the leftmost region, that's -infinity to -3. And I close it and then union 5 to infinity. Okay, let's do one more. Cube root of x minus 4. Cube root means domain is all real numbers. What about this little guy? Well, this 9x minus 2 to the power of 3 over 2, this is actually the square root of 9x minus 2 cubed. That means the stuff inside still has to be greater than 0. So 9x is greater than or equal to 2. X is greater than or equal to 2 over 9. So the domain is 2 over 9 to positive infinity. Okay, the next two are a little bit more involved, okay? Look at this one. 1 over root x plus 2. Okay, first order of business, I see a root. So I say the stuff inside has to be greater than or equal to 0. And then my brain just gives me a warning. And we're like, wait a minute though. Yes, it should be greater than 0. But this time, the root is in the denominator. Can it actually be 0? It cannot be 0. So we say it has to be strictly greater than 0. That's the only difference. So x is greater than -2, and the domain is this. Okay? Yes. Okay. Next one. I have a root in the numerator. X minus 3 greater than or equal to 0, which means x is greater than or equal to 3. Okay? Let's just see what that looks like. It's these numbers. But what is the denominator telling me? The denominator is telling me x cannot be 6 because it'll make the whole thing 0. Where is 6? 6 is here. X can't be 6. So what does that mean? I have to look at this a different way now. I can have the numbers from 3 to 6 and then the ones after, but not 6 itself. So the domain is closed interval 3 to 6 open, and then 6 to infinity. Isn't that cool? Alrighty, I will leave you here today, and I will see you next time.